Hi students, I'm Dr. B. Ravi Kumar, Associate Professor, Department of ECE, Institute of Aeronautical Engineering. Now I'm going to discuss tutorial question bank part 2 from module 4, which is nothing but minimization of Boolean functions. So let us see that what are the possible questions come from this module and how to write the significant answer for those questions. We will see that. Basically, this entire module is the second part from this entire module is discussed from these design steps. So whatever the question is coming from this module, so student, you might have follow these 6 steps, the most important steps to design any combinational circuit, whether that question is coming from like as simple as full adder and half adder, or as complex as implementation of higher like complex circuits like comparator, magnitude comparator, decoder, encoder, muxer, demuxer, or binary code converters, whatever it is. So you might have follow these. You must follow these steps. The steps are: first step is problem stated. Whatever the problem is defined from the given problem. Like if you want to add 2 bits, that is the definition of the problem. If you want to add 3 bits, so we can design the full adder. If you want to data converter or data selector, like among many inputs, if you want to convert like if you want to connect to one output, there is another problem. So if you want to convert from binary to octal, or binary to hexa, or binary to some decimal numbers, or binary to gray code, binary to XS3, that is one problem. So this is the digital circuit, simple digital circuit problems. So, and also in practically, if you want to design a complex problems, it might not be a simple digital circuit problems. It might be a simple user-defined problems which is occurred in the real-time world. So let us see this. What are those steps? Among those, first one is problem is stated. Once you know that clearly describe the problem statement, then you have to define the input and output variables, and the input and outputs are assigned with letter symbols, and then derive the truth table. This truth table gives the relation between whatever the defined inputs and output, and then simplify the Boolean function. The simplify the Boolean function for each output variable in the truth table column. So then once you got this simplified Boolean function, then you have to draw the logic diagram. For example, the question coming from this topic, in the second part of this module 4, construct a logic circuit for full adder. So if you want to design a full adder, you must try to understand this meaning of our definition of this full adder. Full adder means simple adding of 3 bits. So adding of 3 bits is nothing but full adder. If you want to add any multiple bits like 1010 and another 1010, this is a 4-bit data, and this is another 4-bit data. If you want to add in this situation 0 plus 0 0 and 1 plus 1, sum is 1, carry 1. So in this case you have to add 3 bits. So 0 plus 0 0, 0 plus 1 1. This one again here it is 1 plus 1 is 1 0, 1 is carry. So this type of case you require full adder. So full adder means it adding 3 bits. So in this case you can't use half adder. You must use full adder. So that's why it is required to design a full adder. So full adder is nothing but adding of 3 bits. So 3 bits means we have to represent 3 bits means we can represent with the 3 variables. 3. So in the answer you have to first what is full adder, and then define that how many number of inputs and outputs. 3 inputs means 7 possibilities. And what is the corresponding operation of the sum and carry? What is performing the operations? Yes, 0 plus 0, 0 plus 0, like sum 0, carry 0. sum 1 carry 0, sum 1 carry 0, for 0 double 1, like sum 0 carry 1, sum 1 carry 0, 2 ones are there, then sum 0 carry 1, 2 ones are there, sum 0 carry 1, 3 ones are there, sum is 0, sum 1 carry 1. If you add 3 numbers, 1 plus 1, 1 0, plus 1 means you will get 1 1, sum 1 carry 1. So you will get both ones in this triple 1 combination. Then the next step is, so once you create the truth table, then next step is simplify the Boolean function for each output obtained. So there are 2 outputs. What is the Boolean function for S? What is the Boolean function for C? So once we take this K-map, we can create this. The next step is, so this is actually, this is 1, 2, 3 steps are there in this, like four steps from this truth table. Then we can simplify the Boolean function using K-map. Using K-map, we'll take A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. By taking this one, where is the combination of momentum, which is get the logic 1 output in this? 1, 2, 4, 7, 5, 7, 6. So there is no option to combining up ones, logic ones. So everyone is like a independent, so essential, prime implicant. So the S is equal to, so directly we will take that A bar, B bar, C plus A bar, B, C bar plus A, B bar, C bar plus A, B, C, A, B, C. So from this expression, if you want to, like this is like a simply A XOR B XOR C, and carry from this we will get a AB plus BC plus CA. So with this expression, you have to draw the logic diagram. Then you draw the logic diagram for that one. So the next step is, this is 5th step, and the 6th step, take the logic diagram for this one. So how can we draw the logic diagram? If you take this first expression, you have to create, take the, how many number of gates are required? 4 AND gates are required. These 4 AND gates are represented with each minterm. These are connected with a single OR gate, 4 input OR gate. Then you will get some more. And carry, you will take AB BC plus BC plus CA. You will take 4 AND gates, you will connect it with a single OR gates. Otherwise, there is many techniques to optimize this Boolean functions into a simple, like a 2 half adder plus OR gate. You will get also design the full adder. So anyway, construct a logic circuit for full adder, either in a AY diagram or in a, using XOR gates or in half adder, 2 half adder gates with plus OR gate. Next problem, design a 8x1 multiplexer using 4x1 multiplexer. From this topic, I would like to explain what are all the possible questions coming from these topics. Means one way of asking question is, explain with the need diagram, explain the operation of multiplexer and a demultiplexer. In that case, you have to take the logic like block diagram. The block diagram for a simple multiplexer 2 power n by 1. So 2 power n inputs and single outputs, where n is nothing but select lines, n select lines. So for any multiplexer, okay, selecting a 2 power n inputs based on the select lines, then it will be transferred to select one among from the 2 power n possibilities based on the select lines and will be connected to single output. So if you substitute n is equal to 2, so then 2 power 2 means 4x1 multiplexer. So in the 4x1 multiplexer, 4 inputs are there, 1 outputs and 2 select lines. So this is nothing but multiplexer. So once you understood this one, then for example, you have to implement this kind of problem. Design a 8x1 multiplexer using 4x1 multiplexer. this type of question comes, then you know the 4 by 1 multiplexer and we have a availability of 4 by 1 multiplexer, then how to design a 8 by 1 multiplexer. If you in this type of questions comes, so then you have to take a, like you have to follow some condition. That condition is, first how many number of 4 by 1 multiplexers are required to design 8 by 1 multiplexers, then how to draw it. So it is a simple techniques which is nothing but the availability of multiplexers are 4 by 1, that you have to create that 8 by 1 multiplexer. So take that number, that you have to create that multiplexer is 4. You have availability of 4 by 1 multiplexer. If you divide, then you will get 2, and nothing but first level of 4 by 1 multiplexers are 2. Then take that this remainder divided by, like it is 4 by 1 multiplexers. So then, so total number of multiplexers are 2. Take that 4 by 1 multiplexers. 4 by 1 means 2 select lines, 4 inputs, 1 output. This is connected with one simple 2 by 1 multiplexer or simple OR gate. You can connect with the OR gate. Simple OR gate. So here it is 0, 1, 3, 2, 0, 1, 2, 3, 4, 5, 6, 7. So this multiplexer, this 4 by 1 multiplexer, this 4 by 1 multiplexer, we can connect with the common select lines. Common select lines, then you will get this 8 by 1 multiplexer. Sometimes it is required to design higher order multiplexer, like if you want to design this thing with the 2 by 1 multiplexer. Suppose if you want, the question is coming from the design of 8 by 1 multiplexer using 2 by 1 multiplexer. Okay, take that formula. You will create that 8 by 1 multiplexer with the help of 2 by 1 multiplexer. If you divide it, you will get 4, and take that 4, you will get, like you will divide by 2 by 1 multiplexer, you will get 2, and take that 2, divided by 2, you will get 1. So till you will get the remainder 1, until you will get the remainder 1, you will keep doing this process. Whatever the reminders are, then add those reminders. That numbers are nothing but number of lower lower level multiplexer to design higher level multiplexers. So here it is total 4. Add this 4 plus 2 plus 1. You will get 7 number. 7 multiplexers are required. Let us see that how these 7 multiplexers are required to design 2 by 1 multiplexer is using 2 by 1 multiplexer for 8 by 1 multiplexer. So first level is 4 2 by 1 multiplexers. So it is a 2 by 1 multiplexer, means one select line. Two inputs. All are available. 2 by 1. We have a 2 by 1 multiplexers are available. These 2 by 1 multiplexers are connected with the other 2 by 1 multiplexer. Select lines, yes, select line. these two are connected with a single 2x1 multiplexer, you will get the final output. So how to represent this inputs and output and select lines means, basically we have availability of these 2x1 multiplexers, all 2x1 multiplexers. I am representing this one input is I0, I1, and I am providing that to input is I2, I3, I4, I5, I6, I7. So total input is, so our aim is to design 8-bit and finally we will get one output. These select lines are basically 8x1 multiplexer. Our aim is converting this 2x1 multiplexer, connecting this 2x1 number of 2x1 multiplexer into 8x1. So 8 inputs, 1 output, and 3 select lines. How to represent these 3 select lines means, so this first level gates are connected with S0, 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 S0. These two are S1, S1. This is nothing but S3. Suppose any combination if I am giving in the 8x1 multiplexer, suppose select lines in the 8x1 multiplexer S3, sorry, S2, S2, S1, S0. If I am giving 1, 1, 1, all ones, suppose S0 is equal to 1, 1, 1, 1. So this one is by making this 2x1 multiplexer connected to I1, connected to I1, connected to I1, connected to I1. Once S1 is equal to 1, S1 is equal to 1. Here it is 2 paths. Among 2 paths I am connecting this one. In this I am connecting I3. In this connection I am connecting I7. So here it is I7 is connected, here it is I3 is connected. Then S2 is also 1. So one path is coming here, another path is coming here. But by choosing 2x1 multiplexer, I am selecting this lower path to output, so that 7 is coming. So whenever out of 8 inputs, when I am giving 111, 7th input I7 is connected to output. This way you have to design higher order multiplexer with the lower order multiplexer. Construct a logic circuit to convert binary to gray code. So this is one type of question coming from the 4th model. So this problem, this question, convert the binary to gray. So you have to take this definition. You have expect that how many number of inputs. If you convert binary 3-bit binary to 3-bit gray code, 4-bit binary to 4-bit gray code, whatever it is, based on the requirements. So if you want to convert 3-bit binary to 3-bit binary, so you require ABC are the inputs 000, 001, 010, 011, like 100, 101, 110. So XYZ are the outputs to convert gray code. So you know that how to convert gray code. Take the MS bit as it is and the XOR operation of this 0 plus 0 XOR 0, 0 plus 0, 0 XOR is 0, like that. So next to 0 XOR 0, 1, 0 XOR operation 1, 1 is 1, 0 XOR operation of 0, 1 is 1, 1, 1 is 0. XOR operation MS bit take as it is and take the XOR operation of 1, 0. This 1, 0 is 1. Next 0, 0 is 0. Take the MS bit as it is and 1, 0 is 1, 0, 1 is 1. Take the MS bit as it is, 1, 1 means 0, 1, 0 means 1. So this is the truth table. Once you get the truth table, get the Boolean function for X, get the Boolean function for Y, get the Boolean function for Z. Once you get the Boolean function like A bar, B bar, C bar, A B bar, C bar, plus A B bar C, plus A B C bar. So the minimized Boolean function is A B bar common, C plus C bar will get 1. So from this one, A B bar plus A B C bar. So finalized Boolean function is, if A take common, like you will from the K-map, it is very easy to take that one. Take the K-map. Four, 5, 6. We have 7 options also. Take the MS bit as it is. 0, 0. 110, 110. Next, check the 4, 5, 6, 7. 4, 5, 6, 7. So if you take this one, A, B, C, the answer for this one is A, only A. You will get the answer is A. For Y, if you take the K-map for Y, 2, 3, 4, 5. 2, 3, 4, 5. 2, 3, 4, 5. If there are 2 pairs, then you will get the answer is A, B, C. A bar, B plus A, B bar. So A XOR B. And Z, you will take the K-map for Z. 1, 2, 5, 6. It is 1, it is 2, 4, 5, 6. These are the 2 pairs. These 2 pairs can be represented this one. B bar C plus B C bar. So B XOR C is very easy to design. So take the input A to X, same A, B with XOR, B with XOR gate, will get Y. Take the B with C XOR, will get Z. This is the diagram for binary to gray to conversion. So these steps we must mention by following the design steps. So this is the way we can create that you can answer any questions coming from the second part of this minimization of Boolean function or combinational circuits. You can verify these things from the digital design by Maris Mano, and you can collect from the examples from the lecture notes, question bank from this AD from the IARE website. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.